Good morning, good afternoon, or good night, depending from where you are listening to me. I'm going to speak in English, but my text is in Brazilian Portuguese. Today I'm going to deal with electrochemical data. The point is how to extract activity coefficients from electrochemical data. We are going to use Nernst's equation, that is the equation that relates standard potential to potential and the equilibrium constant. And I'm going to show you two simple codes that I'm going to show how to use them, and that will be the chapter. So that's Nernst's equation. That's the Nernst equation, which is actually only this equilibrium equation that we have learned on basic, on a previous thermodynamics course that relates Gibbs energy to standard Gibbs energy and equilibrium constant. If you use the point that the fact that electrical work variation of Gibbs energy at equilibrium is equal to the extra work, non-PDV work, which is in this case electrical work, and it is equals to minus number of moles, Faraday constant, and the cell potential. If you use this fact, this result here on Gibbs, this relation, you get this equation, which is Nernst's equation. The reaction to be studied will be this one, and the data are molality and cell potential, the cell voltage. So how to extract activity coefficients from this data? Also, how to calculate standard cell potential, which is a very important quantity from this data. That will be the discussion. The Nernst equation for this process, since I'm assuming activity coefficients for the gas and solid phase equal nearly to 1, it will involve only the equilibrium constant, will involve only activity from hydrogen plus and the chloride minus. So I get this expression, which is equal to that. If we expand it, we get this one, and if you move this to the left side, we end up with an expression that involves only experimental results on the left and the theoretical results on the right. I have used the Debye-Hückel approximation for gamma, since HCl is a electrolyte of the kind 1 by 1, 1.11. So this left side I will call epsilon experimental, and the right side I will call epsilon Debye-Hückel. And I have to explore the data, the equation 52.4. And I'm going to explore it by two methods. The first one is the graphical method, and the second one is the polynomial method. There is a code here that I will explain soon, but let us analyze how to handle this data. You see, this is a straight line which have slope. If I plot it against molality to the half, this will be the slope, and this will be the point in which the straight line cross the ordinate axis. this will be expression like this. This will be expression like this. And I'm free to change the reference potential, the reference cell potential. I'm going to show it using my program. But here you see I have put this standard potential as 2, 2, 1. I'll get this straight line. These are the experimental results, the data with stars. And you have to try, by trial and error, you have to find the right point here. That is for 2, 2, 1. That's for 2, 2, 3. And it is for 2, 2, 2. Well, I think it's difficult to say, but it is clearly something between 2, 2, 2 and 2, 2, 3. That's the result for 2, 2, 3. And you can see from here that by choosing that, I'm also calculating it, because this point is the point that will fit better the experimental result. That is the graphical method. And now I'm going to show you how to run it in a code. Let's run the code I have just shown. Let's see. The result will be on a graphical form, and this is the result for the straight line with 2, 2, 2. You see touch here. Let's try 2, 2, 1. 2, 2, 1. It's clear not the standard potential. Let's try 2, 2, 2, 3. You see that you have to find the straight line such that it is a continuation of the experimental data near close to 0. Experimental data, of course, cannot be obtained in this region, since there is a logarithm of molality involved if you try to do that. So that's the graphic I have showed in the text. You just have to run the code. In the next step, next item, I'm going to discuss, I'm going to make a fit, a polynomial fit, to the experimental result. And I did it in this way. I have put a series on molality, but starting the half, since the Debye-Hückel approximation predicts that it behaves like, for low concentration, it behaves like m to the power half. So I did this fitting. You see, with two terms, with two terms that are actually the Debye-Hückel approximation, I got these coefficients. I have used this code, and I'm going to explain next how to use it. With three terms, I got that, and so on. But there is a clear tendency for this coefficient, which is actually the reference potential, the cell potential, the reference cell potential, to go to 2, 2, 2 something as before. See, around 2, 2, 3 and 2, 2, 2. And also this number here, it converges to, let's say, 0.05, 0.057 or something, but not to the Debye-Hückel value, which is 0.006. Let's see how I did this program. How you can calculate these coefficients if you want also to go to make these results, to check these results. It's important to say that for this range of data, my residual error is about 10 to the minus 4. I'd like to show how to use this code. That's in my lecture. You see, you can fit a polynomial function by using this command. Just you have to know just a bit of linear algebra. That's the pseudo-inverse, and you can put any power to be fitted. Let's give an example. Let's consider x from 0 to 1, step 0.1, and I generate this data, x squared plus 2x plus 1. And I will try to invert this data. I try to find the coefficients by fitting a polynomial of order 2. If you run this, you get 1, 2, and 1. Let's give another example. 2x plus 1. So I want a polynomial order 0 and order 1. And I get 1 and 2. You see? That's 1 and 2, the coefficients. So here I can find the fitting by using this command. Just the two terms. That's the result I get. Power 1, I add power half, and power 0, power 1. I get this result. And so on. It's very simple. As I said, you have to know only a bit of linear algebra. That's what I'm going to use on the text. There is a side remark I would like to comment that is about this number here. Since under the Debye-Hückel approximation, I get 0.06, but under this fitting procedure, which is very good, I got 0.057. But this constant, I can explore this number in this way. Next item. This quantity, it's not 0.06. I will put this value equal to the one I have found on the fitting. And by manipulating that, I got under 25 degrees centigrade, I got a universal constant, gas constant, over Faraday constant, which is also equal to Boltzmann constant over electronic charge. I got 8.6. And this is a very good result. Very good. I got, for example, suppose I knew Faraday constant. I got R equals that. If I knew electronic charge, I got the Boltzmann constant actually equals to that, which is very good. So, but to decide which constant we are going to use here is not the subject of this lecture. You have to go to the historical facts and analyze it. As I said, it's just a side remark on the subject. Now we have everything you want to calculate the activity coefficient. You have just to invert the Nertz equation to get the activity coefficient in this form. We have already calculated the phi 0. It's given items before. So that's the predicted result. and the experimental one. So our results are good. We are going to make a good prediction on these activity coefficients. Also about the problems, they are quite simple. Just have to follow. I have applied this argument. I used it before. I have used it here for to barometric distribution, to prove the barometric distribution and the chemical potential and the electrical potential. Thank you very much.